Hello everyone. Today we'll start with your third module, that is greedy method. Till now we have studied two different techniques, that is divide and conquer and decrease and conquer. This is one more method we are going to study, that is greedy method. First you have to see what is this greedy method, that is what do you mean by greedy method. A greedy method is a problem solving technique that always tries to find the best solution among the available solutions, considering one input at a time with the hope that we get an optimal solution. Okay, here you must know the optimal solution. What do you mean by optimal solution? Before going for that optimal solution, you need to learn some more things. Here, the problems that are solved using the greedy method are actually called as optimization problems. In this optimization problems, we'll use two things, that is feasible solution and optimal solution. What do you mean by feasible solution? Feasible solution means it is a set of values that satisfies the given constraint. For example, I'll be having some set of values and I'll be having some constraint. Okay, for example, I have a 10 values and I have a constraint. Here, all the 10 values will not satisfy that constraint. Only few values can satisfy that constraint. Only the values which are satisfying the constraint, that will be considered as the feasible solution. And the values which are not satisfying the constraint will be discarded from the list. Okay. And then optimal solution. Yeah, before going for the optimal solution, here the feasible solution, what we have studied, may be optimal solution or it may not be the optimal solution. Always we cannot say the feasible solution will give you the optimal solution. Sometimes it may give or may not give. Okay, see, and next I'll come for the optimal solution. This optimal solution will be obtained by a feasible solution. So only I'm just telling it is a feasible solution that maximizes the profit or minimizes the loss. For example, I have a set of values. I have to find out the maximum profit, okay, which is greater than 500. I have some numbers which is less than 500 also and more than 500 also. The numbers which are less than 500 will not come to the feasible solution. The numbers which are more than 500 only will be there in feasible solution. Among that, which is maximum? For example, I'll be having 550, 600, 700 and 900. Okay, which is maximum? 900 is maximum. Among those feasible solution, the maximum profit you have to select as a 900. That is called as your optimal solution. Okay. In all the problems of the greedy techniques, we have to find out the feasible solution, and from this feasible solution, we have to find out the optimal solution. Now we'll see the algorithm for this one. Yes, see, algorithm greedy A, N. A is the list of inputs and N is the number of input. Now first I initialize solution is equals to null, because till now we don't have any solution. So I'll just initialize solution is equals to null. Then for I is equals to 0 to n minus 1, x is equals to select of A. What you have to do? You have to select an input one by one. First I'll select A. I'll just decide whether it is feasible or not. Then I'll go with B. I'll decide whether it is feasible or not. Then I'll go with C. Likewise, we have to do x is equals to select of A. This select function will select the next input from the list. Okay. Then it will check if feasible of solution x. This function will check whether the selected input can be inserted into the feasible solution or not. If it is accepted and it can be added, then by using this union, solution is equals to union of solution x, it will be added into the feasible solution. Then among all those feasible solutions, we have to select one, what? Optimal solution. That will be done by using this union of solution x. See here, solution of x feasible. If the input is feasible solution, if it is satisfying the constraint, then it will check if feasible of solution s. Yes, if it is feasible, then it will be added over here. Then among these, one will be selected as a optimal solution, and then we have to return that optimal solution. This is how your actual greedy technique work. Okay. Now in this we are going to study so many problems, coin change problem and your Dijkstra's, Prim's, Kruskal's, minimum spanning tree algorithm, Huffman code and knapsack problem. All these are some of the examples of your greedy technique. Now we'll see the first technique, that is your coin change problem. Okay, see here, this is your coin change problem. First I'll tell you what do you mean by this coin change problem. For example, if you just go to a shop and you have purchased something that is of cost 90 rupees and you have given 100 rupees to the shopkeeper, then the cost is 90 rupees. What is the change you have to get? 10 rupees. Here we have so many denominations of our currency. We have 5 rupees, 2 rupees and 10 rupees for this possibility. Okay, he can give 2 5 rupees for your 10 rupees or 1 10 rupee he can give, or 2 5 2 rupee coins he can give to give your 10 rupees change. These things, all these things, 2 5 rupees or 1 10 rupees or 2 rupees 5, these are called as the feasible solution. Among these, you have to just select any one optimal solution which is giving you which is using the less denominations to give you the change. See here, 2 coins they are using, here only 1, here 5 coins they are using. Which is optimal? This is optimal. Giving 1 is better than giving 2 or 5. Okay, this is your coin change problem. I'll just tell you one more time. 5 rupees 2 coins, or 10 rupee 1, or 2 rupees 5. These are feasible solution. Here giving 1 note is better than giving 2 notes or the 5 notes. Then we consider this as the optimal solution. These are all feasible and this is optimal solution. In order to solve this problem, first we have to arrange all the denominations in decreasing order. Means first the highest denomination should come and then the least. See, this is the problem. Let m is equals to 11. Okay, m is equals to 11 means this is the change to be given to the person by the shopkeeper. N is equals to 4 means it is the number of denominations, where denominations is equals to 1, 2, 3 and 5. Okay, find minimum number of coins required to give change for m rupees. Here first what you have to do, you have to arrange the denominations in non-increasing order, that is 5, 3, 2 and 1. It is given m is equals to 11 and then n is equals to 4. Okay, now how will you solve? This is the algorithm what we have, means these are the steps you have to follow. I means the number of steps what you have taken, and then HD is the highest denomination. Highest denomination. You have to check whether that highest denomination is less than your change, that is 11. If it is yes, then you have to do m is equals to m minus HD and then return the value, the denomination as x. Now let me start with the problem. The very first step 1 and highest denomination is equals to d of I. Among this d, which is the highest denomination, 5 is the highest denomination. So I'll just select HD is equals to 5. Okay, now you check HD less than m. M is 11, HD is 5. Is 5 less than m? 5 less than m? The condition is true. Yes. Yes means what you have to do? M is equals to 11 minus 5. What is the value? 6. And if it is yes, then you have to write that highest denomination as x. And here still this is not false. Until it becomes false, you have to just continue with this loop only. So I am not incrementing the value of I. Okay, now you check, is 6 less than 11? Yes, the condition is true. Now do m is equals to What is value of m now? 6 minus what? HD is 5. It is not changed. 6 minus 1 is 5. Again, one more time you add 5 over here. Next, what is the number? 1. Is 1 less than 11? No, the condition, sorry. Is 5 less than 6? Because new m value is 6. Now what is the new m value? 1. So you have to check, is 5 less than 1? The condition is false. It is no. Then what you have to do? You have to go for the next denomination. Now I value will be incremented by 2. What is HD? Highest denomination is equals to 3. Now you have to check, is 3 less than, what is the value of m? It is 1. It will not change. Is 3 less than 1? No. The condition is false. So what you have to do? I'll keep m is equals to 1 as it is. Here no updation. I'll keep it as it is. Next condition 3. Next denomination. HD is equals to 2. Again check, is 2 less than equal to, sorry, you have to just check equal. 2 less than equal to 1? No, the condition is false. M is equals to 1. Then 5 comma 5 will remain as it is. What is the last denomination? It is 1. I is equals to 4. Then HD is equals to 1. Is 1 less than equal to 1? Yes, the condition is true. Then m is equals to 1. HD is also 1 is equals to 0. Add this denomination to x. That is 5 comma 1. Now, what is the change you have to give? 11 rupees. Now, what is the denomination? 5 plus 5 plus 1. That is 11. 2 5 rupee coin and 1 rupee coin you have to give. This is the least number of coins you can use to give this change, 11 rupees. This is your coin change problem. Okay, these are all the feasible solutions what we have got, and this is the optimal solution what we have chosen. This is the optimal solution for your coin change problem. Okay, next let me take one more problem. See here, m is equals to 1, n is equals to 3. Sorry, m is equals to again 11 and n is equals to 3. Denominations are 2, 5 and then 10. Okay, now I is equals to 1. I will take first. HD. What is HD? Here first you have to arrange this 10, 5 and then 2. So HD is equals to 10. Is 10 less than 11? Yes, the condition is true. Then the condition is true. Then what you have to do? M is equals to m minus HD. What is m? 11 minus 10. That is equal to 1. Add this denomination over here. And then next, what is HD? 10. Is 10 less than m? That is 1. Is 10 less than 1? No. The condition is false. M value is 1 now. Here it is 10 only. Then I'll go with the second step. Next denomination is 5. Is 5 less than 1? No. M will remain as it is. And here also 10 will remain as it is. I am not going to add any denominations over here. Then HD is equals to 2. Is 2 less than 1? No, again. Then m is equals to 1 and then here it is 10 itself. See here, there are no more denominations, but still we have 10, but I have to give the change. M is equals to 11. So what you have to do? You have to just say the solution does not exist. This is what I have just told you. Feasible solution may give the optimal solution or may not give the optimal solution. This is the feasible solution which is giving the optimal solution, and this example is for the feasible solution which is not giving the optimal solution. If it is not 0, then the solution does not exist for this one. Denominations got over, but m is still 1. Means 1 more rupees you have to give. Only you have given 10 rupees, you don't have 1 rupee change. So there is no solution for this one. Okay, this is your coin change problem. In the next video, I'll explain the knapsack problem. That is very, very, very important. Okay, thank you.